All right, guys, we're going to continue with our class lecture. We are doing YouTube Live again because I sound terrible and I'm not sure if I can make it through the entire day. But just to review, these are the slides that you're looking at for your quiz tomorrow. You will be looking at covering what's an acid and what is a base. Not necessarily knowing the difference between the Arrhenius and the Bronsted-Lowry definition. If you remember, this one here is the Arrhenius definition, in which we said if you take HCl and you put it in the presence of water, that acid is going to dissociate into a proton and the chloride ion. So the fact that in water you produce H+ ions means that it's an acid. Then we went further and said, I believe it was 1923, Bronsted and Lowry, I think Bronsted was a Swede and Lowry was a Englishman. They came up with the idea through research and saying that an acid doesn't have to produce H+ ions, or not necessarily that, but it doesn't have to be in water. So Arrhenius said that an acid, it had to be, or water had to be part of it. And he said it's not the case. And so what he took the idea is if you took an acid, let's say HCl, and a base, the thought was that the base can accept the proton, which would make it the Bronsted-Lowry base, and then the acid is going to donate the proton. So being a proton donor means that you are an acid. So we would end up with something like this, where now we had the acid, here's the base, here with the BH+, this would be the conjugate acid because it's the result of the base having accepted a proton. And then here's the conjugate base, which is the result of the acid donating and giving up a proton, which that comes down to our definitions down here about the conjugate acid and base pairs. Okay, so the conjugate pairs ties back into the Bronsted-Lowry form of the definition. It's always good to know some of the properties of acids and bases. What was I watching? Sunday, I was watching, we have the PBS app on Amazon Fire TV, and the latest season 16 of Ask This Old House started recently. So I went back and started watching it. I think we watched the first episode and then the second episode, and in the second one, they go out to Arizona near the Grand Canyon, and the guy's having issues with hard water. And come to find out, he had a filter system. It wasn't a water softener necessarily, but the previous owners had left it unplugged. And so he thought it was just not working and it was not plugged in. But come to find out, that specific model, in order to recharge it, like how many of you guys have water softeners on? Okay, we probably should. When we moved into our house, they were renting one, which is odd that you would rent one for so long. And then they removed it, and so now we don't have it. But with the water softener, your parents are putting salt in about once a month, right? So the idea with that is that you have the resin beads that have to be replaced every so often, and then there's like a second part of the tank, and that's where the salt goes in. And so the salt, you're not going to get salty tasting water, but as the water goes past it, it just kind of recharges it and softens it up a little bit. Well, with salt, you're buying a 40-pound bag and putting it in once a month. That adds up over time, right? It can be costly. And the idea with this one thing they had with the filter and the resin is you have to ship it out to the manufacturer every 5 years to be recharged. So then you've got shipping costs. So you've got both of these scenarios where they can get costly in the long run. So what he was showing is this system, and I hope I'm not boring some of you. This was pretty fascinating. So there's two tanks, and In one tank, it's a carbon-based filter, much like your Brita filter has the activated carbon or activated charcoal in it, and that tends to get out a lot of the odors and things that are in water. Okay, so it was basically a big Brita filter on steroids. But I think before it went to, so it went through that one, and then there was one that had citric acid. And I just remember because he's like, here, to the homeowner, taste this. It's like, taste it, citric acid. And he goes, oh man, that's sour. Long story short, acids are sour, guys. That was a long story. It was a really good episode. I might have to show it to you guys, because at least that clip, because there's a lot of the idea of how acids work. Even if they're a weaker acid, which we'll talk about later, they still have an effect. And some acids we can ingest, and there are others that we can't. Typically, your strong acids, we can't ingest. Your weak acids, we can, like acetic acid or vinegar, right? Any of you guys use like apple cider vinegar? It's got a little bit of acetic acid in it. It's definitely sour, but it's not at a concentration that's going to kill you. Same thing with citric acid and some of those. All right. So properties, you should know some of those definitions. You know, we have Arrhenius up here, Bronsted-Lowry, conjugate acid-base pairs. Okay. We also touched on amphoteric substances, the idea that your compound or ion can act like an acid where it donates protons, and it can act like a base. So water, we can add a proton and become hydronium, or we can donate a proton and become hydroxide. So it depends on the context and what we're dealing with, but you can be both. And there is a misconception yesterday when it was asked, what does it mean if a neutral substance is equally acidic and equally basic? A lot of folks in other classes thought, oh, it means that it's amphoteric. It doesn't. You can have an amphoteric substance. It doesn't mean that, you know, if you test the pH of that solution, that it's going to be at 7. Okay? So neutral is pH 7 when concentration of protons. When the concentration of protons and hydroxides are the same. Okay? And that's down here where water ionizes. So they're saying water ionizes to form H plus and hydroxide. So they're saying that when it does that, the concentration of H plus and the concentration of hydroxide are the same. They're equal. And if they're equal, then you're considered neutral because you're equally acidic and basic based on concentration. Okay. This concept here is a good one to be familiar with for the quiz tomorrow. And as I said, the quiz is going to be pretty darn similar to that half sheet of practice that you had last week that we discussed yesterday. It's going to be pretty similar. When we talk about pH, we've got some of the important pH formulas. In fact, I have them all written up on the board right now. I'll leave that up on the board for tomorrow, and I'll give you the quarter sheet that's laminated that has the formulas on them, so you can use them for that and for the test next week. What's next? Okay, let's I guess pause for a moment. And what I'd like to do is just bring up a sample problem, because I'm sure that we do need some practice still. So here is the practice problem. Given a hydroxide, an OH concentration that equals 2.6 times 10 to the minus 4 molar, what is H plus concentration What is pH? And what is the pOH? Okay. So take a moment. Remember, it doesn't matter which order you go in, because the way the formulas work, we can go any which way. But work on them. I'll be around to look. Mr. Rob will be around to take a look. Anyone else want to calculate a calculator?
Oh, I didn't. Are you doing two months? Oh, Yeah.
All right, guys. So as we're given hydroxide concentration, there's a few directions that you can go to solve. And as we walked around the room, we saw just that people went in different directions. But one thing I was saying while I was out there was we're given hydroxide. If we look at the different equations that were given of these six, which of these six allows us to plug in hydroxide and solve for something else? If we look, this one allows us to plug in OH, where we can solve for H+, which we want to find in A. And POH equals negative log of hydroxide. So if we plug in hydroxide, we can get POH, which is what we want in C. Okay? So we can go that direction. If we start out with A, if it's this times hydroxide equals 1 times 10 to the minus 14, then we're going to do H plus equals 1 times 10 to the minus 14 divided by the 2.6 times 10 to the minus 4. And I believe this came out to what, 3.85 times 10 to the minus 11. Okay.
Minus 0.1. I don't know why, but it came out. And I like to do this.
Okay.
I accidentally messed up.
Did you do 10 to the minus 4 instead of minus
I
14?
had minus 14 instead of.
Oh, for right here? Okay, that would make sense. Riley?
3.84 times 10 to the negative 19.
You would get that if you somehow added your exponents together. So did you multiply, did you do this times this? Parentheses are our friend. It's going to sound very sad on video. Parentheses are our friend. All right, so now that you have H plus, we could either go from OH and find POH and then work backwards to pH, or we can take H plus and find pH, which would be negative log of H plus. I like this route because then what that enables me to do, even though I write out the 3.85 times 10 to the minus 11, I don't have to clear the calculator. I can just go to the next step in the calculator and type in negative log answer to get my pH, which I think is 10.6, 10.42. All right, I was kind of close. So 10.42. And then remember for POH, pH plus POH equals 14. So if we plug in our 10.42, 14 minus 10.42, which is 3.58. Okay, so that's the POH, and that's going in order from A to B to C. If you set it up differently, remember that POH is negative log of hydroxide. So if we plugged in negative log of what we were given, 2.6 times 10 to the minus 4, what that equals is 3.58. And then we could have done this equation here to find pH if we just solve for POH. So we could go from C then up to B. So your order of solving doesn't really matter, which can be troublesome for some students because they like a very regimented, rudimentary, straightforward approach. Like there's only one right way, and this gives us multiple ways to get to this end result. Okay? Did these practice help? Okay. Let's go back and look at our slides. All right, so right now we're going to take a look at strong acids. So strong acids says some acids that fully ionize are not reversible and are said to be strong acids because they have many H plus ions present in solution. So many H plus ions present in solution. And they're usually more hazardous, and the reason is that in solution we have more H plus ions around, more protons. So an example here, if I have an acid, I'll just write HA as my generic acid, is in the presence of water, you are going to get H plus and A minus, right? The proton and then the conjugate base. What we notice here is that we have a single directional arrow, which tells us that this dissociation or dissolvent event is complete. from start to finish, it goes from acid to ions directly. It does not go in between. There's no equilibrium. It's just that it goes to be complete, so it is not reversible. It fully ionizes. Right? And so because you have many of those protons present in solution, they are generally more hazardous because you have more of them around. Okay, some examples of strong acids. We have hydrochloric acid. We have sulfuric acid. We have nitric acid. And we have perchloric acid. Okay, so those are the names that go with the formulas. So the idea here is if we were to set this up so that it dissociates into its ions, it would fully ionize. For example, sulfuric acid in the presence of water completely ionizes into 2 protons and a sulfate ion. Okay, and that arrow is going in one direction, which says that that yield or that reaction is complete. You guys remember when we defined equilibrium last unit? We said that when products are a lot more stable than the reactants, the reactions go to completion. And when the products aren't much more stable or aren't a lot more stable than the reactants, then we set up equilibrium because we get a reversible reaction. We can go forward and we can go back. So strong acids are the example where the products are a lot more stable than the reactants, and so we go to completion. The case where we get a reversible reaction is with weak acids. These are acids that break apart into ions and then recombine to form the original compound set up as an equilibrium. What this means is that we have an incomplete ionization, which means it's less than 100%. Okay, and it's less than 100%. You can have an acid that 99% of the acid dissociates into ions, still considered weak because it's not 100%, it's not complete. You can have an acid that dissociates 5% of the time. That's still a weak acid because it's not complete. The idea here says there are fewer H+ ions present. These acids are considered to be weak, which means they're usually less dangerous to work with. Okay? And it comes back to the amount of H+ ions that are present. Okay? So an example for the weak acid is if I have some acid HA, now what we see is we had this equilibrium set up. It's a reversible reaction. So we're going to have protons and A- ions, and we're going to have our acid around 2. Okay? And it can be anywhere from 1% all the way up to 99.9% ionization. It's still weak because it's not 100%. It's not complete. Okay? Do we understand the difference between strong and weak so far? Right? The key part is for strong, you have something that fully ionizes. Okay? And they are not reversible. Those are strong, and again, you have many H+ ions in solution, so it's considered to be a stronger acid, which is a lot more dangerous because you have more protons. And then a weak acid, you have fewer protons in solution, so it's not going to be as strong or as dangerous to work with. Okay. If we look at it in the context of bases, strong bases fully ionize. And then weak bases are reversible. They set up the equilibrium. Same context as strong acids and strong bases. So strong bases, you have 100% ionization. Weak bases are less than 100%. Okay. Some strong base examples you have here. We have sodium hydroxide, potassium hydroxide, and calcium hydroxide. And one thing we had said before too is that a lot of bases have hydroxide. If you have a base or an acid, at least from the Arrhenius definition, if one has hydroxide, you're making hydroxide ions. If one has H, you're going to make the protons. Okay. So that covers strong acid and strong base. So what we can look at next is strength versus concentration. And then we're going to briefly define neutralization. And so actually, based on your slides, we only have 2 slides left for today. Right? All right, so strength versus concentration. We've talked so far about strength. If something is strong, you have 100% ionization. If it's weak, you have less than 100% ionization. So for strength, we'll do, I guess, strength in blue here. Strength refers to the extent that ions form from the compound. So how many H plus ions are we forming? Are we doing 100% or not? How many hydroxides for the base? Is it 100% or not? That's talking about the strength. Concentration refers to how many moles of solute there are per liter of solution. Okay, so back to unit 2 of solutions, we're saying how many moles per liter of solution are there? So what's important here to realize is that we can have a strong acid and a weak acid and have an equal concentration of both. In other words, we can have the same volume and the same amount of moles of each, and one of them will be more dangerous than the other. And that deals with the strength component. So then the strong acid is going to have more H plus ions in solution than the weak acid. Okay. So you can have the same amount of moles per liter, same concentration for both, but the extent to which they dissociate into ions determines the strength. So that's why it says here that a high concentration of a weak acid can still be safer than a low concentration of a strong acid, because you might have a lot of moles per liter of a weak acid, but there's still going to be fewer H plus ions in solution compared to the low concentration of the high strength, or the strong acid rather. Okay. So that's the key difference between strength and concentration. Again, the strength, to what extent are we dissociating? Are we doing 100% or not? And concentration is how many moles per liter. So you can have equal concentrations. One will be more dangerous than the other because it dissociates more. Straightforward as that. Okay, turn the page. All right, so neutralization, just as far as the definition, when an acid is added to a base, the products are always salt and water. And remember, as a note, and I've said this a lot of times, that salts are ionic compounds. So any ionic compound that we have, that's a salt. Okay? We often think salt is sodium chloride. It is a salt, but so is copper sulfate or iron iodide. Those are all salts. So anytime an acid and a base are combined, the idea is that we're going to get a salt and water, okay, generally. And for the neutralization, for the base, we're talking a base that has hydroxide. Okay, so we're looking at an areneous acid and an areneous base for this neutralization. So what happens is, if I set it up here, let's say HCl and potassium hydroxide. Okay, the H from the acid is going to go hang out with the hydroxide, and then the cation is going to go be with the anion, the chloride. You may remember from Chem 1 that this is considered a double replacement, specifically an acid-base neutralization. So when we take these partners, we said the H is going to go be with the OH. On the other side, we get our KCl, and we get the water, H2O. Okay? So that's neutralization. When you have the acid and base, the H goes to be with the hydroxide to form water, and then our other substance is the salt made of the chloride anion and the potassium cation. I think really what you need to know for neutralization is the products of a neutralization. Folks. Salt and water, congratulations. I believe you just earned 6 points out of 60 on your assessment next week. I've done that in the past where I just make it a ridiculous amount of points at the end, and some folks still get it incorrect. I'm like, come on. Salt and water. Salt and water, salt and water, salt and water, salt and water. Make a song. Salt and water, salt and water. Okay. I'm going to end there for today. All we have left on here really is salt hydrolysis and buffers. And we're going to cover the salt hydrolysis after your quiz tomorrow. And then Friday, we'll take a look at buffers. And then that'll be it for the week.